Hello, this is lecture 10 for week 10 of Psych 1040, and it's the week that we introduce the t-test. So let's talk a little bit about this. Well, what we've gone so far is we've been talking about hypothesis testing, and last week we specifically focused on what happened when you have a mean rather than an individual score. And I introduced the z-test for doing this and how we could look at the sample mean and figure out whether or not our sample mean was different from what the hypothesized mean would be for the null hypothesis. Now, the z-test that we used was particularly useful when we know the population standard deviation. And if you go back and look at all of the problems that I covered in lecture and also what we did in the workshop, every example I already gave you the population standard deviation. That is, it was known. And this is really not the case usually in the real world of psychology. That is, in psychology, we tend not to know what our population standard deviation is. We have to estimate the population standard deviation. And this is quite frankly makes a lot of sense because a lot of times we're actually making up new measures, new dependent variables, and we wouldn't know if the population is what the standard deviation of that population would be. So we, again, take our sample's standard deviation and we make an estimate. If we were to give this measure to everybody in the population, what do we think the population standard deviation would be? Well, because we're estimating it, that means we can no longer use the z-test. And in fact, what we usually use in psychology instead is what's called the t-test. So the t-test is when we don't know the population standard deviation, but we're going to estimate it all the same. Now, before I get started, this is going to sound like it's some sort of advertisement, but it's not. It's actually this. It's Guinness. And Guinness is what brought you today's lecture. Now, the reason why did Guinness bring you today's lecture is because Guinness is actually responsible for the statistics that we're learning today. Guinness was part of the origin of the t-test. And so we're going to talk a little bit about that. And then maybe later on, much later on after I've recorded this lecture, I'll have a little bit of this Guinness very good stuff. Now that you've seen how Guinness beer could be possibly related to what we're going to be talking about today, let me explain to you what Guinness beer's role is in statistics. It has to do with this guy that's pictured here, somebody who was working at the Guinness brewery. His name was William Seeley Gossett, who lived from 1876 to 1937. He was a brilliant mathematician and statistician who happened to have a job at a brewery. And one of the things that he had to do was take small samples from different ingredients that were going into making the beer. And he became sort of obsessed with this. He had to have these small samples and then try to draw inferences about what was going on in the population of whatever it was. So for instance, if he was looking at the best varieties of barley to use in the beer, he would have to take small samples of barley from different farmers and then try to make an estimate or make an inference about what it would be like in the entire population of barley there for that farmer before they would go ahead and buy that crop and then use it in the beer. So in this sort of very practical problem of brewing Guinness beer, Seeley develops the test that we're going to talk about today, the t-test. So he develops this t-test and he also develops the t distribution that goes along with it. The unfortunate thing for him, though, is that he wasn't really free to share who he was to the academic community. And I think this is partly because Guinness wanted to keep his identity secret. They didn't want to have any nasty academics out there. So what he did was he ended up publishing papers on his new statistical technique for mathematics journals. And he published these papers under the pseudonym Student. So student became his pseudonym, and in fact, after that, people referred to these new t-tests as student's t-test. And you'll still see that occasionally if you look in a textbook or if you look at it in some online forum, you'll hear the t-test referred to often as student's t-test. We now know that it was actually Gossett who did this, so you could call it Gossett's t-test, but the name still lingers. The student t-test has to do with his pseudonym. All right, let's go ahead and talk a little bit more about why he did this. Why did he develop this t-test? Why was he forced to do this? And it comes back to that problem of the fact that he didn't know what the population standard deviation was. He realized he couldn't just use his z-test to do this, that he would be off a bit. He would not be estimating it properly, and therefore, because of that, his calculations might be off when he was actually trying to make inferences again about the population. So how does a t-test differ from a z-test? Well, there are three ways that it does. A t-test uses an estimate of the population standard deviation based on the sample standard deviation to produce an estimate of the standard error of the mean. So this means that we're going to be using that n-1 version of the standard deviation formula to produce this estimate of the population standard deviation and therefore produce an estimate of the standard error of the mean. Another way that it differs from a z-test is that, unlike a z-test, each t-test has associated with it a certain number of degrees of freedom that's related to the sample size and the number of parameters that are being estimated. So I'll be introducing this new formula for what's called the degrees of freedom. A t-test is based on a t-distribution, whereas a z-test is based on the normal distribution. So these last 2 points go together. We have this new distribution to introduce today that's going to have a slightly different shape based on the number of parameters that are being estimated. And in this calculation of the parameters that we're looking at, we'll get something called a degrees of freedom that I'll talk about in more detail in a moment. And the degrees of freedom are then used when we're looking at our t-distribution to figure out where our cutoffs are and that kind of thing. So let's take that first point about how the t-test differs from the z-test and use this estimate of our population standard deviation to produce an estimate of the standard error of the mean. So in hypothesis testing, we normally want to use this comparison distribution to do our hypothesis testing. And because we often are making inferences about means, where we go ahead and say in the null hypothesis, for instance, that the mean is not different from 0, we usually choose the distribution of means as our comparison distribution. Now, when you know the population standard deviation, sigma, then you can use the formula that we covered last week to compute the standard error of the mean. So that's the formula that I showed you last week. So if I want to get the standard error of the mean, I know the population standard deviation, I can go ahead and take it and divide it by square root of n. I can also, by the way, if I have the variance, the population variance, I could have that as sigma squared, and I could put that into the formula and take that over n, and then take the whole thing under a radical, and I get the same thing. So either way, if I have the population variance or I have the population standard deviation, I can get my standard error of the mean. But again, this is all when we know the population standard deviation. But what about when we don't know the population? When we do not know the population standard deviation, what you do then is you use S, our estimate of the population standard deviation, to compute an estimate of the standard error. So here's our S. Now the S again is the formula for the standard deviation where n-1 is in the denominator in the formula. So we would go ahead and use that as our estimate of the population standard deviation, S. Then we take that and divide it by square root of n. And you can see that we now have this new symbol, S sub m, which stands for an estimate of the standard error. So now we have an estimate of what we think the standard error is like out there in the population of the distribution of means. But it is not the same thing as what we had before because we're making an estimate. So here's our formula that we introduced this week now when we don't know the population standard deviation. Go ahead and use your sample standard deviation as the n-1 version of the formula, and then divide it by the square root of n, and you'll have your estimate of the standard error. Now, keep in mind too that my second and third points are that the shape of this comparison distribution is different. So it doesn't necessarily follow a normal curve. And in fact, what Gossett found was that the distribution of means when you're estimating the population standard deviation isn't the shape necessarily of a normal curve. It's a little bit off. And what he determined was that when we are estimating it, the distribution of means follows what he called a t-distribution. Its exact shape depends on the degrees of freedom that are used to make the standard error estimate. In this case, its degrees of freedom is equal to n-1, okay? So we are now using or introducing this thing called degrees of freedom. So let's just take a slight detour and talk about what degrees of freedom are. And it's sometimes italicized here as like df. So this n-1 correction has this special name, degrees of freedom. And this refers to the number of values that are free to vary when we're estimating a parameter. Now, it might be a little hard to understand what we mean by free to vary. So let me give you a really simple example. For example, let's say that we have a formula in which the formula says you have to choose 4 numbers that add to 100. So I have this thing set up where I have 100, and let's say I pick 25, then I pick 20, or then I pick 25. So now I've picked 3 numbers, And now you'll notice, though, that the fourth number has already been predetermined by the fact that I picked the other three. So my first three choices were all free to vary as much as I wanted, but my fourth number here has to be 30, right? So 25 plus 20 plus 25 plus 30 equals 100, and therefore I would now have that formula work out. If I tried again, and if this time I decide that the first time I'll pick a 50, the second number I pick a 20, the third number I'll pick a 10, my fourth number, I don't really have a free choice here. What actually has to happen here is that I have to have 20 be my answer in order for it to work. And finally, when I have 10 plus 80 plus 5, then you can see that the only answer I can have there is 5. So in all of these problems, even though it looked like I was free to choose any four numbers that I wanted, I only really had 3 degrees of freedom. Only 3 of the numbers really were free to vary, and the fourth one was always determined by whatever the other 3 happened to be. That's basically what's happening when we talk about degrees of freedom here in estimating a parameter. And it's a little bit more complicated than that, but for now, just accept the fact that for every formula where there's some sort of estimate of a population parameter, there will be a degrees of freedom associated with it. And that means then you'll have to look to see, for instance, on the t-test, there's some different degrees of freedom for different kinds of t-tests. But the statistical formulas usually include a formula for computing the degrees of freedom. So you don't have to go and try to figure it out from scratch. You don't have to actually go through all the logic of a t-test to figure out how many values for free to vary. And instead, there'll be just a formula that comes along with it that tells you what the degrees of freedom are. Okay, so going back to what we were talking about with the t-distribution. So here's what student, or I should say Gossett, figured out about the t-distribution. What he did was he figured out what the distribution of means would look like when we're estimating population standard deviations. And you can see that the mean of this distribution is always 0. So a t-value has a mean of 0 in the middle of the distribution. And then you can see we have more extreme values that go from -4 to +4 out in the end. So in some ways, this looks a lot like the way the z-table looked like, where we had our z-scores and the middle of the distribution was a 0, and we could go up to 3 or 4 standard deviations and then get really, really rare out there. Same thing's true here for the t-distribution. Now you'll notice, though, that the only curve that's on here that's actually defined as a normal curve is the one that's sort of the light blue that's down at the bottom where it says standard normal. So the light blue is an actual normal distribution. All of the others are t-distributions for different degrees of freedom. So for example, we could pick degrees of freedom of 1, and you can see the more darkish blue is the one that sort of sticks in the middle there. It doesn't kind of reach up all the way to the top where the normal distribution would be. And also you'll notice that the tails kind of stick out a little bit higher on that particular curve. The red one represents degrees of freedom of 5. Then we have a light green that's degrees of freedom of 10. And when we get to the purple, you can see that the purple one, degrees of freedom of 30, is almost exactly right on top of a normal curve. It turns out that different degrees of freedom under 30 really do vary quite a bit away from the normal curve, but the closer you get to degrees of freedom of 30, the more it starts to take on exactly the shape of a normal curve. And in fact, you get to a high enough level, it is actually a normal curve. Okay, so that is what a t-distribution looks like. And in order to figure out what the cutoffs are, you can go out there and find t-tables. We don't have one for the textbook that we're using right now, but the t-tables are freely available. You can look on Google and find them. Here's one that I like. It's actually got the t-tables for one-tailed and two-tailed tests. The table itself is just showing you numbers for two-tailed tests. And so it says here the level of significance, alpha level for a two-tailed test. So if you pick that middle column of 0.05, everything you see down below the 0.05 are different cutoffs for different degrees of freedom. The place where the tail would be a place where we could say anything beyond that is so rare when the null hypothesis is true that we'll reject the null hypothesis. Then you can also see the cutoff for 0.01 and 0.001 in the far right column. So we have plenty of choices here, again, just like we had with the z-test in terms of where the cutoff is going to be. The main difference, of course, though, is that we have degrees of freedom now. So for every curve up to 30, we're going to have to know what the degrees of freedom are to look at it appropriately and find out where the cutoff is. Notice again that when you get to the very bottom of this table, it's got a little infinity for the degrees of freedom. So yes, if we reach infinity for degrees of freedom, you can see that the values for the cutoff, like look at 0.05, 1.96. Now that number should look familiar to you because 1.96 is the cutoff when we were using an alpha 0.05 in a two-tailed test, that we had plus 1.96 and minus 1.96 on a normal curve in the Z table. Well, it turns out, like I said to you, that in a t-table, the t-distributions actually do finally reach at infinity the level of having a normal curve, and you get the same exact cutoffs. Everything between 30 and infinity is really, really close to 1.96. It's just a matter of just a little smidging, a little bit different, a little bit away from that. Okay, so I want to again emphasize, just from looking at that table, since it only goes up to 30, that Gossett really created the t-test for small samples. So when he was dealing with small samples, that's when he ran into this particular problem that estimating the population standard deviation could have in terms of figuring out whether or not it's a significant difference. And so that's why we like using t-tests when we have these smaller samples. Okay, now I've given you a lot of the logic behind the t-test. Let's go ahead now and look at a specific t-test. And we're going to start off with one that's very analogous to the one we had last week. It's called a single sample t-test, okay? So just like last week, we had one sample mean and we wanted to test it to see if it was different from some known value. We're going to do the same thing here, except of course, we're not going to know the population standard deviation. So what we'll do is we'll use a table of t-values, and since there wasn't one in the textbook, I've actually made a copy of the one that I just showed to you on Blackboard. But you can use that table then to determine the cutoff scores for t when you're deciding to reject the null hypothesis. Or when you're using a program like Jamovi or SPSS to do your statistics, that will actually give you the probability of the t if the null hypothesis were true. So you'll find out exactly what your probability is and be able to make a determination then whether or not you want to reject the null hypothesis. And I'll show you that later in this lecture. So let's go ahead and work through a computational example with a single sample mean. Here's one where you can do this one by hand. And let's say that we've read that the typical year 12 student can identify 32 out of 70 countries on a map of the world. You give this test to 10 students in your year 7 geography class. And the question is, are your students different from the average year 12 student? Maybe you're a teacher that has a fancy new way of teaching geography, and you want to see if maybe your year 7 students are already better than a year 12 student. So you want to go ahead and test whether or not they're doing much better than a year 12 student. We just want to know if they're actually really different. So now notice that in this problem, I didn't actually tell you what the population standard deviation was. We're going to have to get that from the sample of 10 students. Okay, so that's how we're going to figure this out. So I will go ahead and present to you what the data look like. Like I said, we're going to use this t-test to hypothesis test. And so here are the data. We have 10 students, and I have their 10 scores on this geography test. There's somebody who had a 61. There's our highest score. But if you go ahead and look through all the 10 x's and then we add them up and divide by 10, you can see the adding up turns out to be 425. So if we divide by 10, our mean is 42.5. So that means that these 10 students had an average score of 42.5. Now, in order to do my calculations to figure out what my estimate of the standard deviation is, I've gone ahead and created 2 more columns over here where I took each person's x and subtracted the mean, 42.5, from it. So I've taken 32, subtracted 42.5, 59, subtracted 42.5, and so on, and figured out all those values in that column. And then finally in the last column, I took those numbers and I squared them. So all of this is just creating those steps that we need in order to be able to get our estimate of the standard deviation. And you can see down there the sum of those different scores squared, differences squared is 1268.5. Okay, so I want to go ahead and just take these numbers now and turn them into some values that I can use. If I want to know what the mean is, like I've already showed you, I take that sum of x, 425, and divide it by 10. Now, if I want to figure out what the variance is, the estimate of the variance is for the population, I could take that sum of the x minus m squared and divide by n minus 1. So I take 1268.5 and I divide by 9 because I'm using the n minus 1 correction to estimate the population variance. And that comes out to be 140.94. I can also compute the s by just taking the square root of the s squared, right? So if I take the square root of 140.94, I come out with a value of 11.87. So now I have my estimate of the population standard deviation, 11.87. So those numbers I worked out first, and now I can go ahead and begin my hypothesis testing. And step 1 is to restate the question as a research hypothesis and a null hypothesis about the populations. So if my students are just like those year 12 students, that means that their mean is 32, right? The year 12 students. So I'm going to go ahead and say that the null hypothesis is that mu is equal to 32. My alternative hypothesis for now will go in either direction. I just want to know that they're different. So I'm going to go ahead and say their mu is not equal to 32. So there's my statements of my population parameters. Now in step 2, I want to determine the characteristics of the comparison distribution. So I've gone ahead and made a little table here to kind of work this out. So to figure out the population mean of my population when it's when the null hypothesis is true, the mu would be equal to 32. So if I think about that comparison distribution, the distribution of means, the mean would be 32. Now keep in mind now for the variance or the standard error, I'm going to have to estimate those based again on my samples. So I'm going to estimate the population variance and therefore the population standard deviation. And so I get my estimate of the population variance, the S squared. I've already done that. It was 140.94. And then I need to take the square root of that to get my S, or 11.87. And now at the bottom, you can see how I would go ahead and compute my standard error. I'm going to go ahead and take that 11.87 and divide it by the square root of n. Now it's important that you see that we're using n here when we talk about our estimate of the population standard deviation. We already did our n-1 correction when we were estimating the population variance or estimating the population standard deviation. So once I already have that estimate, I'm just going to go back to using the n now when I make my estimate of the standard error. So I take my S, 11.87, and I divide it by the square root of n, which is 3.16. Then that means that my estimate of the standard error is now 3.75 based on this sample of 10. Finally, I can look at the shape of the distribution, and I know that this sampling distribution of the means, this comparison distribution, has a T shape, a T distribution when the degrees of freedom is n-1. So I'll have to look that up in the table for degrees of freedom of 9, because that's what I have here, 10 minus 1, 9, to figure out what my cutoffs are. So hypothesis testing test step number 3 is I want to determine the significance of the cutoff using the t-table. And again, here's that table. I'm going to go ahead and use alpha 0.05 two-tailed, so I can just go right down the middle of the page there where the 0.05s are and find where the degrees of freedom is equal to 9. And I can see that my cutoff is 2.262. Now this is two-tailed, and t's can have both positive and negative values. So I want to imagine then that I'm going to have a cutoff above the mean of 2.262 and one below the mean that's minus 2.262. Or the way I have it drawn here, I have my t distribution where the degrees of freedom is equal to 9. And I've gone ahead and marked off the cutoff where 2.262 is and minus 2.262. All right. And I can write that down as well. Instead of just using the picture, I can say the cutoff for degrees of freedom of 9, two-tailed, p is 0.05 is plus or minus 2.262. Step 4, determine your sample score on the comparison distribution. Now my sample mean, remember, for these 10 students is 42.5. So I'm going to go ahead and convert that to a t, just like I would have converted it to a z before. Again, the difference. In the denominator, I have an estimate of the standard error. So very much like a z-score, I convert things to a t-score. I take my mean, 42.5, and I subtract the mean when the null hypothesis is true, which is 32. So 42.5 minus 32 is 1.44. And then down the denominator, I have my SM, my estimate of the standard error, and that's 3.75. That's something I computed earlier. So I put that in the denominator, so I get 1.44 over 3.75, and my t comes out to be 2.8. So where is that in the distribution? Well, that's way out here in the extreme, right? So it's off to the right in the tails. There's the t of 2.8. So all that's left to do now is in step 5 is decide whether or not that exceeds my cutoff. Do I reject the null hypothesis? And you remember that my cutoff was plus or minus 2.262. So since our obtained t was greater than 2.262, we can say that we've rejected the null hypothesis, that our students are somehow different from those other year 12 students. Because again, here's our t and it's exceeded the cutoff. This happens less than 5% of the time when the null hypothesis is true, so we reject the HO. And if I'm going to go ahead and write this down, I could report it in APA style by saying something like the year 7 students differed from the year 12 students. T, and then in brackets I put my degrees of freedom, which in this case is 9, and then it's equal to, and then I give my T that I actually computed, which was 2.8, and I say the probability of getting that is less than 0.05. Now, another statistic that I introduced last week was this thing called the effect size. And you remember that a very common measure of effect size is Cohen's d. So we can actually compute a Cohen's d for this problem. Cohen's d is defined as, in the numerator, the difference between the means divided by, in the denominator, the standard deviation. So here, the difference between our sample mean and the tested mean, the one that the null hypothesis said, is going to be the thing in the numerator. And then in the denominator, we're going to use our estimate of the population standard deviation, our S. Okay, so we're not going to use our estimate of the standard error, just the estimate of the population standard deviation. So to work this out, our Cohen's d for this problem would be 42.5, because that's the mean of these students, minus 32, which was the mean defined by the null hypothesis. So that's 42.5 minus 32. Divided by 11.87. And the 11.87 comes from our S, our estimate of the population standard deviation. So I plug that in there, and I come out with my Cohen's d of 0.88. Please note that if you instead use the estimate of the standard error and put that in the denominator, Cohen's d would be equal to the t. So that's not what we want. We just want this thing in the denominator to be the estimate of the population standard deviation. So my Cohen's d is 0.88, and I therefore could amend the way I report this to fully report it as the year 7 students differed from the year 12 students, t brackets 9 for the degrees of freedom equal 2.8, comma, p less than 0.05, comma, and then I have an italicized d to show that I'm talking about a Cohen's d, and it's equal to 0.88, which is a fairly large effect size. And just to tell you the truth, that in order to have these small samples give us significant results, we usually construct fictional examples to have large effect sizes, so that's why it's such a big effect size here, 0.88. All right, let's go ahead and look at another problem. This problem is different, and see if you can see how it is. Rachel has designed an experiment to test the effects of subliminal messages. While waiting for the experiment to begin, she measures the number of times participants yawn in a 10-minute period. Then she tells the participants that she'll be playing a recording that they should listen to while they sit in their chairs. During the next 10 minutes, music plays through the speakers, but embedded in the music, someone whispers, "Yawn, you feel like yawning," over and over, and she again measures the participants yawning. So what you can see here is we really have 2 times that the participant is measured. One time while they're sitting there waiting for the experiment to begin, we record the number of times that the participant yawns. And then during the next 10 minutes, when the music is playing through the speakers, and there's someone saying subliminally, "Yawn, you feel like yawning," we're also measuring the number of times that they yawn. So we got 2 10-minute periods for each participant. This kind of analysis is different from what we had before. This is called a dependent or a within subjects t-test. Let me break it down a little bit more. So imagine again that we're collecting some data from these participants. So when we have the 10 minutes when the recording wasn't playing, and then 2 minutes when the recording was playing. So we've got 2, 3, that's one person. And then another person's got 1 yawn, and then 2 yawns. The next person, person number 3, has 0 yawns and 0 yawns, and so on. So in the end, what we have are a bunch of scores, but what we're going to analyze is the difference between those 2 scores. So what we're really going to do is look at different scores. So for instance, I have 5 participants listed here, 2 and 3, 1 and 2. So again, this is when they're listening to the recording, right? And so you can see here that I'm going to go ahead and take the first time, their baseline that happened during the first 10 minutes, and subtract that from what happened when they were actually listening to the recording. And so I've got 3 minus 2, that's 1. 2 minus 1 is 1, and so on. And so the different scores represent, how much of a change was there really between the second time and the first time. And that's what we end up analyzing in this t-test, are these different scores. So even though there's 2 scores from each person, we're going to go ahead and compute a different score. So that's just a new score that we get from that person. It's just the difference between the 2 scores. Laying this out into more of a table, you can see here I have now my fully 10 participants in the study. When they were listening to no recording, I call that X1. And then when the recording was playing, that's their x2. So I have the number of yawns for x1, the number of yawns for x2. And I find that for all 10 people. And then you can see I can sum up down at the bottom, and they could therefore figure out what the mean is for each of those two for x1 and x2. But I really want to focus on that third column, or sorry, here in the fourth column, the difference, the x2 minus the x1. So I'm going to take each person's x2, subtract the x1 from it, and put the difference there. And you can see now in red that 3 minus 2 is 1, 2 minus 1 is 1, 0 minus 0 is 0, and so on. I do have participant number 6 who had 1 yawn when the recording was playing, but 2 yawns when it wasn't. So they end up getting a -1. And it is important to pay attention to whether or not the difference score is positive or negative and how you define it. But you can see that the mean number of yawns that I had when no recording was playing was 0.8. The mean number of yawns recording when the recording was playing was 1. And that the difference then, the mean difference is 0.2. So we had a 0.2 increase in the amount of yawning that happened. But because this t-test is just going to focus on those difference scores, we no longer have to pay attention to x1 and x2. We'll just pay attention to the differences in that column. And so just like I did before, I'm going to go ahead and do some more computations here so I can figure out what the standard deviation is. And what I would do then is take the difference minus the mean and square it. So I go ahead and take the person's 1, that's their difference. And then the 0.2 here that I'm subtracting from it is the mean of the differences. So my mean difference is 0.2. So I take 1 minus 0.2 and I square it. And that ends up being 0.64. So what I've done is I've taken the difference, the deviation from each person's difference score, subtracted the mean of the different scores from it, squared it, and then I got 0.64 and then 0.64. And for the zeros, even that comes out to be 0.04 and 0.04 and so on, until I get to the bottom and where I can sum them all up. And I have now the sum of those square deviations, and it's 5.60. So I'll be able to use that to figure out the standard deviation and my estimate of the standard error, just like I did in the previous t-test. So let's try to take these numbers now and finish them out doing the 5 steps of hypothesis testing. So if we start again with the step 1, restate the question as a research hypothesis and a null hypothesis. Well, this time what we're going to do is we're going to say, well, if the tape or the recording of the subliminal messages it doesn't have any effect, that would mean then that the mean of the differences for a population that had no effect of the recording would be 0. So the mu of the difference scores would be 0 out there if there is no real effect of this recording. If, however, the recording does have an effect on yawning, that would mean that the mean of the differences is not equal to 0. Okay? So that's our alternative hypothesis, that the mu of the differences is not equal to 0. So there's step 1. Let's go to step 2. Determine the characteristics of the comparison distribution. So just like I did before, I'm going to go ahead and figure out what the population mean is, the population variance, my estimate of the standard error, and the shape of the distribution, based on the numbers that I have that came from the problem. So in order to figure out what the population mean is, it's just going to be based on what the null hypothesis says. So the mean of the differences is 0 according to the null hypothesis. The estimate of the population variance is based on that 5.6 that I got, that sum of the deviation squared, divided by n minus 1. So I had 10 participants. I'm going to subtract 1, and now I get 9. So that would mean that 5.6 divided by 9 is 0.62. So if I take the square root of that, I now have my standard deviation of those different scores. It's 0.79. So I now have an estimate of the standard deviation of different scores out there, out in the population. It would be 0.79. But I want the standard error of that comparison distribution. I want to know the standard deviation of the distribution of means for this kind of t distribution. So in order to do that, I have to find an estimate of it. And so I'm going to go ahead and take my estimate by taking the s-diff 0.79 and dividing it by the square root of n. And so again, the n here is the full 10 people that I have. So I'm going to go ahead and take 0.79 divided by the square root of 10, which is 3.16. And then that gives me an estimate of the standard error of 0.25. So there's my SM of those difference scores, 0.25. And finally, the shape of the distribution, well, it's a t distribution because I'm estimating the standard error. So I'm going to look this up in a t-table. And I'm going to look up when I have degrees of freedom of 9, because again, I have 10 participants, n minus 1 is 9. Okay, so I've done all the work of figuring out the characteristics of my comparison distribution. Step 3 is determine the cutoff using the t-table. And this is going to look eerily similar to the last t-test that we did because I have the same degrees of freedom. I'm going to use alpha of 0.05. I'm going to do a two-tailed test. And if I do all of that, again, I come out with that thing right there in the middle, 2.262. That's my cutoff. I'm going to get plus 2.262 and minus 2.62. I'm just doing this again on the difference scores, right? So there's my cutoff. When the degrees of freedom of 9, it's 2.262 at the top, minus 2.262 on the bottom, right? So there's my cutoffs, stating them in words rather than through a picture, plus or minus 2.262. Step 4, remember, is that I need to figure out what my sample score is on that comparison distribution. Now my sample mean is 0.2. That's the mean of the different scores that I got, 0.2. Mu of the differences is 0 here because the null hypothesis says that the mean of the different scores will be 0. And then I divide that again by my estimate of the standard error of the different scores. So I've got 0.2 for my mean of my differences, minus the 0, which is what the null hypothesis says. And then that's divided by 0.25. That's how I figured that out in the previous step, that I figured out my estimate of the standard error was 0.25. So my 0.2 divided by 0.25 gives me a t then of 0.8. That's not a very big t, and you might remember that the cutoffs here are 2.262. So my obtained t is a little bit above the mean, but it's nothing very extreme. It's something that would happen quite frequently when the null hypothesis is true. So deciding whether to reject the null hypothesis, I'm going to say that my obtained t, because it was 0.8, does not exceed the cutoff. Therefore, I conclude that I do not reject the null hypothesis. So I say that I have no effect of my subliminal message. So there isn't any effect here. Okay? And you could work out what the statement would be that you would write on the APA style and also what the effect size would be. These are our repeated measures designs. When I go ahead and I have the same participant being measured 2 times, it's also called a within subjects design. So that's why you also hear it called a within subjects t-test. And sometimes it's done when the same, well, obviously here, the same people are tested twice, maybe before and after some procedure like a pre-test and a post-test design. Or it could be when there are 2 conditions in an experiment and the same people are tested under both conditions. Or you sometimes see this used when you have different people that are matched together somehow in pairs, like maybe it's a married couple, or it could be that you're talking about identical twins. So you think that there's some sort of connection between 2 people. So you have their score for one person, the score for the other person, and you do that for all of your participant pairs that you have. That would also be a within subjects or a dependent t-test. So any of these kinds of designs would use this kind of t-test. The key thing, the thing I hope that you're picking up here, is that it's not really that different from a single sample t-test because all we're doing is analyzing the difference or the change score, the difference between x1 and x2. In our example on subliminal advertising, we just determine the differences for each person in those 2 conditions. But this could also be used if we were looking at their pre-test, post-test score, if we were looking at what twin A says and what twin B says and so on. So it's all the same. It follows the same things whether we're talking about a single sample t-test or a dependent t-test. We're just doing it now with different scores. Here's a nice little summary table that takes you again through the 5 steps. Remember, number 1 is to restate the question as a research hypothesis and a null hypothesis. And then we had this whole thing about determining the characteristics of the comparison distribution. Notice that in the figures listed here, we don't actually have that subscript diff, like the way I wrote little diff in there before, but it's now about different scores. And so all of that you see here, the writing here, works for the same as when we had a single sample t-test. So the t-test for dependent means and the single sample t-test have basically the same logic. It's just that here in the dependent means t-test, we're looking at differences between the 2 scores. Now, finally, I just want to mention that there are some assumptions to these tests that underlie why we use them. And the assumptions, by the way, assumptions are circumstances that must be true for the logic and the mathematics of the statistical procedure to work properly. The major assumption for the t-test for dependent means is that the population distribution of these different scores should be normal. It must be normal. We're assuming that that is out there in the population. We don't know for sure because usually, like I said, we have no idea what's really going on in the population. All we have is our sample, but we're just going to assume that our sample basically reflects what reality is out there in the population. So it's not usually a problem unless we find that our population might be quite skewed because of some sort of dependent variable that's really skewed, or that I'm using a really small sample size. Those are times where this assumption could be called into question. So that's something to be important to pay attention again to when you're plotting your data and you see that it's, for instance, really skewed or it's got some other weird shape that doesn't look a normal curve. It might not be appropriate for you to be using this particular test. All right, I want to go ahead now and show you how to do these same t-tests that we did by hand, how we would do them in Jamovi. So Jamovi allows us to do t-tests. It can do a single sample t-test or a dependent t-test. So here's our single sample t-test example that we can do in Jamovi. Imagine we have a Dr. Zeppo who's teaching Psych 1040 a new way this year. His course usually has an average final grade of 67.5. But he's introduced weekly TikTok videos to his teaching this semester for a group of 20 lucky students, and they end up having a mean of 72.3 for their final grade. Are they indeed scoring higher than normal? Is this what we normally would expect if you are just in a regular course of Psych 1040, or is maybe TikTok actually having an effect? So let's walk through the 5 steps of hypothesis testing, amended here for Jamovi. That is, I'm going to slightly change things because we don't have to work out everything by hand now if we're going to use Jamovi. For step 1, it is the same, where I can basically make statements again about populations and parameters. I can imagine that population 1 is just students who take Psych 1040 the usual way. Population 2 would be students who are somehow affected by having TikTok videos, so they're different, they're in a different population. The null hypothesis would be that the mu is equal to 67.5 because that would describe population 1, right? They usually have a mean of 67.5. The alternative will be that no, they're not like that. They're different, so their mu is not equal to 67.5. Step 2 is to determine the characteristics of the comparison distribution. We know again that this comparison distribution is going to follow a t-distribution because we have to estimate our population standard deviation. It wasn't given to us in the problem. Step 3 is that we're going to choose to do a two-tailed test with an alpha set of 0.05 because nothing else was said in the problem about that. We didn't have necessarily a directional hypothesis. So let's go ahead and just set it up to be a two-tailed test, alpha 0.05. Nothing else has to be looked up at this point. We don't actually have to find any cutoff values or anything like that by looking it up in the tables because everything else will be given to us by Jamovi. Step 4 is to determine the sample's score on a comparison distribution. We're going to do this again using Jamovi to find what the t-value is for our sample, and we'll also find out its probability. So when we get to step 5, we can make a decision whether or not to reject the null hypothesis. All right, so I have my file open for Dr. Zeppo's class, and you can see that there are 20 students in the class. Here are their IDs in the first column. And then we have their grade in the course. So these are the 20 people who took the course now with TikTok. And again, the question is going to be, do they have a mean that's different from what you would normally expect if the null hypothesis is true? So the way we analyze this, we click here to t-tests under Analyses. And one of the choices is one sample t-test. So I pick that. And once we've got that set up, we can go ahead and down here and pick different things. So let's go ahead and say that our dependent variable is going to be their x. That's their score for their grade. And you can see that it's already starting to generate some stuff over here, but it's not actually correct yet because I haven't finished putting down what I need to do. Now, my hypothesis is that I'm going to test to see that they're not, that they're different from 67.5, which is what people typically get in this class. I put in 67.5 and I'm testing to show that I'm not picking a particular direction, whether it's above or below. I'm picking that it's just not equal to 67.5 in my alternative. So I put 67.5 here. Now, if you look here, a couple other things I can do is I can pick the effect size, all right? And if I want, I can also put the descriptives. So I've done all that now, and you can see that over here I have my one sample t-test. and your student's t. The statistic is 2.25. So the t that I've obtained, the one I would report in the article, is 2.25. My degrees of freedom is 19, and that makes sense, right? Because we had 20 students in here, and now we subtracted 1, so we get 19. The p-value is 0.036. So this is telling you exactly what the probability of getting 2.25 or higher is. It's definitely below 0.05, right? So if our alpha was set at 0.05, then 0.036 is clearly exceeding that, and that would mean then that we could reject the null hypothesis. And finally, I have my effect size, my Cohen's d, it's 0.504. I also have some descriptives here. There's my mean, 72.3, my median, 75, and my standard deviation, the estimate of the population standard deviation, 9.52, and my estimate of the standard error, 2.13. So everything's there that I would have done by hand, but just quickly was done on Jamovi. So coming back to our 5 steps of hypothesis testing here, amended for Jamovi, let's go to step 5, deciding whether or not to reject the null hypothesis. Again, if the probability of our t-statistic is less than what we chose for our alpha, if our alpha is 0.05 and we get a t-statistic that's less than 0.05, we're going to reject the null hypothesis. And in this case, we got a p-value that was less than 0.05. It was 0.036. So we can reject HO. And so if I'm going to write this out in proper APA format, my conclusion would be that the students in Dr. Zeppo's course who have weekly TikTok videos are different to the students who have the normal Psych 1040 course, comma, T, then in brackets, again, I put my degrees of freedom, 19, equals, and then my obtained T, the T that was computed here was 2.25, comma, I can give the p-value, the exact one that was given to me in the output of my Jamovi. It was 0.036, so I can go ahead and say that, 0.036, comma, and then give my Cohen's d. My d is 0.504, full stop. So now I have the results of my Jamovi for doing a t-test for a single sample mean. Let's move on now and try to do the same thing for a within subjects t-test in Jamovi. So we'll have a slightly different data set this time. This data set comes from Dr. Chico's class. In her class, students take 2 major tests, one early in the semester and one later in the semester. To hear her tell it, she runs a very hard class, one that most students find very challenging, but she argues that by setting hard assessments, students are encouraged to work harder. So her theory is that the first test is a bit of a wake-up call for students. And when they realize how hard her class really is, they'll work harder for the second test and get a better mark. So the question is she right? Is this really having an effect? Do people really do significantly better on their second test than they do on the first? So let's set this up again with our 5 steps of hypothesis testing, again, amended for Jamovi. So step 1 is to make some statements about the populations and parameters. And remember, we're really thinking again here about the differences between test 1 and test 2. So population number 1 is going to be students who show no improvement between the 2 tests. That would mean that there's really no difference between test 1 and test 2, whereas population 2 is students who show an improvement between the 2 tests. Now I'm going to test this one with a directional hypothesis. I'm going to actually try to say this isn't just about being different, it's going to be being different in a positive way. So my null hypothesis this time is set up to be the mean of the differences for the population here is equal to or less than 0. So that is, I think that people who show no improvement are going to have a mean that's equal to or less than 0. Whereas if you actually are doing better than on your second exam than the first grade, the mean of the differences then would be greater than 0. So I'm going to have a directional hypothesis, which you're going to see is going to make it into a one-tailed test. So my mu of my differences is greater than 0. Step 2 is to determine the characteristics of the comparison distribution. Now we again can talk about this being a t-test because we have to estimate the population standard deviation. This time when we determine the significance of the cutoff, we're choosing a one-tailed test, again with alpha set at 0.05. Nothing else has to be looked up again. We don't have to go and check anything out on a table, but you'll see that when we're in Jamovi, we can pick that we want to do a one-tailed test and we'll be able to see the output then for a one-tailed test. Step 4 then is to determine our sample score on the comparison distribution. So we're going to use Jamovi to find out the t-value and its probability. So let's move then to Jamovi. So here are the data for Dr. Chico. You can see again, we have 20 students and we have their IDs, their student 1 through student 20. And then I have 2 scores from them, their grade on test 1 that happened early in the semester and their grade on test 2 that happened later in the semester. And so again, we're interested in seeing whether or not there's a significant improvement from grade 1 to the test 2, right? So the grade test 1 to the grade test 2. So in order to analyze this, we're going to go back up here and click t-tests again. This time, we're going to go ahead and pick a paired samples t-test. So that's what's called in Jamovi a dependent t-test or a within subjects t-test. Is the same thing as a paired samples t-test. So I click paired samples t-test. Now I'm going to do a couple little things here. I want to set it up so that I have this directional hypothesis that they do better on grade test 2 than they do on grade test 1. So where it says here paired variables, I'm going to say what are the 2 variables that I'm going to be testing against. I'm going to go ahead and stick the first one in here as test 2. And then what I'm going to do is say that the other variable that I'm comparing it to is test 1. So you can see I have grade test 2, grade test 1. And already you can see that Jamovi is trying to get ahead of the game here and telling me what is going on. I want to go ahead though and also pick a directional hypothesis. So this time I'm going to go down here where it says hypothesis, and I'm going to hypothesize that measure 2, that is grade test 2, actually, sorry, I'm going to do the opposite way, that measure 1, which is grade test 2, is greater than measure 2. So I click this, and you can see now that I have a directional hypothesis where I'm saying that what their score is on grade test 2 is greater than what it is on grade test 1. So I have a directional hypothesis that I'm picking here. A couple other things again I can pick is, because I'm looking at different scores, I can pick and find out what the mean difference is by clicking this button. And I can also pick their effect size by picking this. And then finally, if I want, I can do descriptives. And you can see now for the descriptives, I have the mean on grade test 2 and I have the mean for grade test 1. And you can see that, yes, on average, they're doing better on grade test 2, 58.4, than they did on grade test 1. Is it a significant difference? Well, back up here to the results of my t-test. I can see here it says to students T. That's the statistic I've got was 6.48. My degrees of freedom is 19. And the p-value I got is less than 0.001. And that's simply because I have it set to only go to 3 digits, and it's probably even smaller than 0.001, much smaller, but it's just rounded it to p less than 0.001. So this is a very rare event to occur when the null hypothesis is true. My mean difference is 1.40, so that's how much it went up from test 2 to test 1. And here's even the standard error of my different scores. So that thing that I would estimate as my standard error. And finally, here's my Cohen's d, my effect size, 1.45, which is quite large. One thing I'll just tell you right now, this is a little handy trick, but if I go ahead and click, right-click it or use my control click on a Macintosh, I can say copy. And what it does is it actually copies that entire table. And then you can paste it into Word exactly like that. And it does a nice job of that. It's an APA format, in fact, when you do that. So for your problem set this week, I'm going to ask you to go ahead and paste your Jamovi output into your problem set. And so the way you do that is just from what I did there. Is you go ahead and do a right click or control and clicking on it, and then say copy, and it copies that table. And then it's in your clipboard, and then you can paste it into Word or whatever document that you're using. Okay, so that's it for Jamovi. Let's go back to what we were doing with our problem set. With our hypothesis testing. So coming back to our 5 steps, number 5 is to decide whether to reject the null hypothesis. And it turned out that yes, our probability of our t statistic was definitely below 0.05. In fact, it was below 0.001. So we can reject our HO. And you can see here that it says students in Dr. Chico's course do better on the second test. I can say that in a directional way, comma, t, then in brackets again I wrote 19 is equal to 6.48. That's the t that Jamovi computed for us. I give the probability, and Jamovi is just going to round it to 0.001, so I just say p less than 0.001, and that my effect size is a whopping large Cohen's d of 1.45. So that's, again, how I'd report this in APA style. So now you've seen 4 different t-tests in this one lecture, both for single sample means and for a dependent t-test. But I say that they're all basically the same because they're really just one set of numbers that are getting analyzed, whether we're talking about difference scores for the dependent t-test or the single sample means in the single sample mean t-test. And we did it both in hand calculations and we did it in jamovi. And when you do your problem set this week, you're going to do the same thing. You're going to do some problems by hand and you're going to do the same problems again on jamovi. So go ahead and try it. I hope it goes well. That's it for now. And next week, we'll talk about the independent t-test.